So I'm going to move on to a second data set that I have as well. So we're gonna use the Madagascar data set still, but there's another data set I want to look at as well. And this is let me open it in, let's see right here. So you also have this data set as part of what I sent. And this is the weights of chicks, baby chickens. And we have a couple different variables in here. So this was an experiment that was set up so that we have, let's see, we have a total of 50 chicks in this data set. They're labeled 1 through 50. And the chicks were, as soon as they were born, were put on different diets, so different types of feed. And the idea would be that we would want to see if they gain weight differently. So if the chicks that are on diet 1 ended up weighing more than the chicks that are on diet 2. So we have their weight when they were born, and we had their weight, I think this was after about 3 weeks. So we have their weight before and their weight after 3 weeks. Then we have just another categorical variable in here that we can look at. I categorized this to indicate whether the chick was above average when they were born and whether they were above average after 3 weeks. So we can look at whether the diets, we can look at their actual weights based on the diets, and we can also look at whether they are above average based on their diet. Okay, so let's get back now that we've seen what this data set looks like. We're going to keep using the Madagascar data set, but we're also going to start using that chick weight data set. So first I'm going to chick weight. Actually, let's just let's do that. Chick weight was to read.csv. So I'm going to read in the chick weight data set the same way that I read in the Madagascar file earlier. And remember, this only works like this because I've set my working directory, and it's going to look in that folder for this file. If I didn't set it, then I would have to give it a full path name so it could find that file. But now I can double check, and I have this chick weight data set, and it looks like it just did when I opened it in Excel. Okay, so we're going to start, we're going to actually hop back to the Madagascar data set. We're going to start with a very simple test, which is a one sample t-test. You maybe haven't done a one sample t-test in a long time, if you've ever done one. So the point of a one sample t-test is to look at one mean, not to compare, but to look at one mean and determine if that mean is different from a specific value. So one question I might ask, so let's say that we consider somebody who is 18 or older to be an adult. Maybe I'm interested in seeing if people in the Madagascar data set, if they were 18 years old when they migrated, or if they were different from 18 when they migrated. So they tend to migrate when they became old enough to move, or do they have a different average age? And the way that I'm going to do this, I don't need a package. This is already part of R. I'm just going to write t.test. Sorry, there's no quotes there. I need to put quotes in there. And I'm going to say, oops, age at migration. So that's all I need to do. T.test, Madagascar $age at migration. And then if I don't type anything, this test will test to see if their age is different from 0. I don't care if their age was 0. I want to know, though, maybe if their age was 18. So I have to put in one more thing. I have to specify the mu, or the mean, that I want to test against. So I'm going to see if they were 18 years old. Okay, so here's the results that R gives me. It says, here's my t-statistic, -3.1. I had 55 people in the data set, so my degrees of freedom is 54. And I have a p-value of 0.003. Now that's small enough that we would generally determine that means their average age was not equal to 18. And R even tells me this, the true mean is not equal to 18. R gives me a confidence interval for their actual age. This is a two-sided confidence interval because I didn't specify less than or greater than as my alternative hypothesis. And this says First of all, their average age is 15.25 when they moved. And they are the confidence interval for their average age is 13.5 to 17. So there's a question now for, again, I have sort of applied a Western standard to this, saying 18 is when you're an adult. And so these people moved when they were younger than 18, so they might not have been considered adults. But in this culture, that could be different. So this is something I'd want to look at more before I wrote a paper about this. But it looks like most of them moved when they were younger than, or the average age at which they moved was when they were younger than 18. Now let's say that I already had an idea and I was like, I think they were probably younger than 18 when they moved. I can specify an alternative hypothesis. And again, if I want to see what's available, I can always do help.ttest and I can see I have different alternatives I can use. So I could say alternative equals less if I want to test whether they are younger than 18. So let me go ahead and run that. Okay. And when I do that, of course, my p-value is smaller. This is something that we know about how t-tests work. If you specify the direction and your hypothesis, your alternative is supported, then you'll have a smaller p-value than if you run a two-sided test. And now I get a one-sided confidence interval that basically says we are 95% confident that they were younger than 16.7, and I still get the same mean. So we can use this to test, again, just a one sample t-test. More commonly, though, we use t-tests to look at pair differences or to look at comparisons across two groups. So I'm going to show you how to do that. Interestingly, so let's say that I want to see if two groups have different means. So let's say I want to see if the age at migration was different based on gender. So did males and females tend to have different ages at which they migrated? I can use the exact same function for this. I don't have a different one for an independent t-test. It's just based on what information I put over here inside the parentheses. So I'm going to specify Madagascar dollar age at migration because I want to, that's the variable that I want to see if it's different. And this is the first kind of formula that you're going to see in terms of statistical analyses. I want to know if age at migration is different based on gender. And so we can kind of think of this as the dependent variable, and this as an independent variable. I know we don't tend to think of that as being a situation for t-tests, but basically I put the thing I want to look at on the left side, and then the tilde, and then on the right side, the groups I want to compare. And I can, let's see, I don't have any specific hypothesis. I just want to see if the ages could be different or if they could be the same. So here's my independent t-test. And if I look at the output here, notice it says this is a Welch two-sample t-test. I'll talk about what that means in a second. But here's my t-statistic. It's 2.6. Here I have degrees of freedom, each group size -1, and then add it together, so it's 53. And my p-value is, again, small enough that we would probably say that these two ages are not the same. A confidence interval for the difference gives me 0.99 to 7.51. And I can see here's the average age for females. They were on average 17 years old when they moved, and males on average were about 13. And so this is the confidence interval for female minus male in terms of how much older they were. So there's my two-sample t-test. Now the Welch t-test does not assume that you have equal variances in the two groups. A lot of times when we learn the two-sample t-test, we learn a version of it with equal variances. So that's an option I can use here if I want to say, let's assume that males and females have equal variances in their two groups. The option I can use here is var.equal equals true. So I can tell it to use the same variance for the two groups. It changed my p-value and my confidence interval a little bit, but overall, I basically get the same result. And then the final t-test that I want to look at is the paired t-test. So the reason I wanted to have the chick weight data is because we have two weights and we have two categorical outputs for each individual. So for the paired t-test, this is kind of a silly test because we should know that the chicks are going to weigh more when they are 3 weeks old than they do when they're born. But just to show you how it works, once again, we use the same function. I still use t.test. It's just in the way that I write it that R knows that I want to do a paired t-test this time. So I'm going to do chick weight, weight 1, chick weight, weight 2. So those are the two variables that I want to see if they're different from each other for the same individuals. And just to make sure that R understands, I say paired equals true. So that's the option we use when we want to make sure R realizes this is a paired t-test. And I run that. I have my t statistic. It's very big. Again, we know that chicks are going to weigh more at 3 weeks old than when they are born. We have a very small p-value here, and so we can conclude that yes, they do weigh more at 3 weeks than they do at when they hatch. Okay, so that's for testing numeric variables. I want to look at categorical variables next, so looking at how we can determine whether proportions are different, but I think I'll take a break and ask if people have other questions. It can be about what I've been doing or because I know there might be some trouble with the audio. Just any questions that you have about R and how I use it. So does anyone have any questions that they'd like to ask? No questions right now? I'm having trouble hearing. No questions. Okay, I'll keep going. Okay. And I should mention too, I am recording this, so you'll have the video available if you're having trouble hearing. Okay, so the next thing is looking at categorical variables. All right, so let's say that I'm going to look at the Madagascar data set again. One of the things we have is their religion. Everybody was categorized as Protestant or Catholic. Catholicism is very popular in Lavatinina, but there are some Protestants as well. And so let's say that we want to see if males and females tend to have different religious preferences. So what we want to think about there is, okay, we want to see if, when we think about do they have different religious preferences, what we're talking about is proportion of males who are Catholic and proportion of females who are Catholic. And we want to see if those are different. So the most common test that we use for that is a chi-square test. In this case, we can think of it as a chi-square test of independence. So is religion independent of gender? But we use the same thing for homogeneity as well. So let's take a look at this. The code here is just CHISQ, CHISQ .test. And just like we've already seen, you might guess that we would put in the, let's do religion first, no, religion, that we would put in just the two variables that we want to look at. So this should starting to look kind of familiar, which is religion and age, or religion and gender, sorry. And Here's the results that we get. There's not as much given to us in the results as there was for like the t-test. So you'll see it just gives us our chi-square of 1.4, our degrees of freedom, which is just 1 because it's a 2 by 2, and a p-value of 0.2, which is not very small. So we would not conclude really that there's evidence that there's a difference in religious preference based on gender. Now, of course, we've already seen how to make a table. Let's see, religion. And I'm going to say, all right, so let's say that let's do 2. So this shows me if I want to, like, again, just showing the chi-square test is okay, but I probably also want to be able to look at the actual proportions of each of these two genders that claim each religion. So I can see among females, it's 60% Catholic. Among males, it's 78% Catholic. It's not the same, but there's not enough statistical evidence for us to say that they're different based on that chi-square test. What if I want to, I want to show you a different example. You might be aware that sometimes a chi-square approximation, if you have a very small sample in one of your groups, it's not considered very good. So I want to give you an example of what you'll see. Like, let's say, because I think maybe more than gender, maybe religion will have to do with, let's see, maybe we'll have to do with where you want to be buried. Maybe, maybe if you are Catholic, you're more likely to want to be buried near your family. I don't know why that would be, but it's possible. So let's say that I try to look at something like this. If I look at, let's do religion, let's do dollar desired burial, and let's look at religion. So we can see, for example, that 83% of Catholics want to be buried in the city, 78% of Protestants want to be buried in the city. That's a small difference. But one thing that we can see, if we just look at the table itself, is that we have some very small groups here. So, for example, I have only 4 Protestants who want to be buried outside of Vavatanina. This is a very small group, and so the chi-square test might not be a very good test. The chi-square approximation for that statistic might not be very good. And we can see that, so R did give us a result. It gave us this very big p-value, which makes sense because this doesn't look very different. But it also gave us a warning message. And so this is why we always want to read everything that R tells us and not just look for specific things. Because this is telling us that the chi-square approximation may be incorrect. And so if I see that, again, I might look at this table and say, oh, we've got a very small sample size. And in that case, a different test that we can use is a Fisher exact test. And that's going to look exactly the same way. Is it lowercase? As the chi-square test, and write Fisher.test. And this could be more appropriate when you have a very small sample size in one of your groups. And so this gives me a p-value. It also gives me an odds ratio for comparing the two groups to each other. Okay. So there's one more situation that we might have 2 categorical variables that we want to look at. And one of those is the, if we look at the chick weight data set, let's say if I want to see if being above average at birth makes a chick more likely to be above average in terms of their weight at week 3. So we can do that with a McNamara test. This is different from what we saw in the Madagascar data set because we're comparing different individuals. Here I want to compare proportions, but for the same individuals at 2 different time points. And so the test we can use for that is the McNamara test of symmetry. And again, this function is just part of base R. You don't need anything special for it. Chick weight above average 2, chick weight above average 1. So what this is going to do, again, it's going to compare to see if the chicks that are above average at birth tend to be above average at week 3. And here's the results of this. This is a pretty small chi-square statistic and a pretty large p-value. So there's no evidence, especially if you don't account for the diets. There's no real evidence that a chick that is above average when they're born will still be above average at week 3. Okay. So that is all of the basic categorical analyses that I was going to cover. I think I do still have time to at least get started looking at linear regression and maybe ANOVA. There's a little bit more material in the lecture that I may not have a chance to cover, but you do have all of the syntax and handouts as well, so you can always go on to look at those examples too if we run out of time today. So let's look at linear regression. So this is where we really move into another level of statistical analysis in R. And a lot of, so what we've done so far is just kind of some basic comparisons. Linear regression, we really think of that more as a model. So we're moving into statistical models now. So let's say that I want to know, so again, in the Madagascar data set, I have this variable called link importance. And this was a variable that we created to measure how important the individuals felt that their connections to their family in the country were. So this was not like necessarily how often they were connected to their family, but just how important they felt that was. And so we might want to see if their current age is related to how important they think those links are. So maybe someone who is older finds it more important to be connected to their family than someone who's younger. So here's how we do linear regression in R. So the function that we use for it is LM. LM stands for linear model. So this is the same one that we can use for ANOVA or ANCOVA or general linear models. It can be used for a lot of different types of linear models. And what I'm going to do, we already kind of saw a formula like this. The outcome, or we could think of it as the response or the dependent variable, is going to go on the left side, just like we write it in a textbook. So we're going to say link, we're going to say, and this is going to be a little different than what we've seen before. So far, every time I've mentioned a variable, I've had to do this. I've had to name the data set and then give the variable. Here, I don't have to do that, and I'll show you why. We're just going to say the output is link importance. So that's I should probably spell that correctly. Link importance, and the predictor is age. I want to see if age, another numeric variable, is related to link importance. And then the final thing that I put here in this formula is I name the data set. And I'm using the Madagascar data set, so I'll write it like this. Let me show you what happens if I run this. So it gives me an intercept and a slope. So I can see from this, there's maybe a negative relationship of age to link importance. For each additional year of age, the link importance goes down a little bit. So maybe the younger people are slightly more likely to consider those links important. But what this does not give me is a lot of other important information. It doesn't give me things like standard errors. It doesn't give me p-values. It doesn't give me a lot of those. If I want all of those, this is one thing that at first seems very weird about R, especially if you're used to using something like SPSS, where you run a procedure and you get a lot of output and that's it. If I want more information about this model, I have to save it as an object in R. So I'm going to say, I'm just going to call this model 1. Very creative name. You can name it anything you want though. I'm going to call it model 1. I'm going to run this. And now you can see that I have this and it saves it under data. I have something over here called model 1. I'm going to click on it. This is not the easiest thing to understand about R. There's all these different things, though, that are now part of this model that I can request and get information about. So, for example, I have residuals, and I can show you model $1 residuals, and now I can see all of the residuals from this model. So if I wanted to do something, and I'm going a little bit off script here because I know I don't have as much time as I thought as I wanted to, but I can make a histogram of these residuals, for example, or a QQ plot. Sorry, I have to say QQ norm. And so I can look at my residuals because I saved this model. I think the most important thing, though, that you want to look at first is maybe the ANOVA table from this model. So that'll tell me, for example, age. Here's my statistical test of age. I have an F value, I have a P value, and I have things like the sums of squares and mean squares. So that I can get because I now have this saved. I can look at the summary from this model. So this gives me more information and things I'm used to seeing from a linear model. So I have an estimate of the intercept and the slope, which we already saw, but now I have things like standard errors and p-values associated with those. This tells me my R-squared, which is pretty small, and tells me about my, my residual error. So all of those things, just the key is to remember that in order to really look at all of the things from a linear model, you have to save it as an object and then ask for things like the ANOVA table and the summary. All right, let's see. ANOVA. We can also do ANOVA using LM, the same thing. The trick with ANOVA, so I'm going to use the chick weight data and check to see if their weight at 3 weeks, so weight 2, is related to their diet. So I'm going to set up my second model. I'm going to do the same thing. Not link importance, it's going to be weight 2. And I'm going to set, so weight 2 is my outcome or my response variable or my dependent variable. Diet is my categorical variable that I want to use in the ANOVA. And of course I have to say, now that I'm using LM, I have to specify the data set. Chick weight. Now, I'm going to run this incorrectly to show you what happens. And if I look at the ANOVA for this, you'll see I have diet just has 1 degree of freedom. My chicks have 4 diets, and I know that's not right for an ANOVA. So this basically treated it as if this was a continuous variable, the same way it did for regression. So I'm going to, the thing you have to do to make this work is you have to make sure, so R is a little different again from some other software. I don't specify in the linear model that diet is categorical. I have to do that in the data set. So I'm going to say chick weight $diet, and I'm going to as dot factor chick weight $diet. Okay. So before I run an ANOVA, I have to make sure that my categorical variable is saved as a factor in the data set. So what I'm doing here is I'm saying, hey, make a variable called diet based on the old diet variable, but this time make sure that it's a factor. And now if I run this and I look at the ANOVA, I can see I have 3 degrees of freedom for diet, and that's what I want. It shouldn't be 1, it should be 3, since there are 4 diets. My p-value is pretty small. If I look at the summary for model 2, I can see coefficients. I'm missing diet 1, so that's my reference level. I'm not sure how many of you will have seen that way of writing a categorical model. But these are comparing, these p-values here are comparing diets 2, 3, and 4 to diet 1. If I want to get more information, a lot of times we want to see other tests. So I don't just want to see, is diet significant? And I maybe don't want to compare everything to diet 1. There's a package we can use to look at what we call estimated marginal means and to get contrast. So I'm going to, you would have to install that package, which is called EM means. I already have it, so I don't need to install it, but I do need to library it. So now I have access to that, and I can say, oops, EM means model 2, and then I have to say what variable I want to see the estimated marginal means for. And I want to see them for diet, and I have to write it like this. This tilde reminds R that that's the independent variable. So now I can see here for each diet, the lowest weight is for diet 1, the highest weight is for diet 3. I get confidence limits for those. And then if I want to do all the pairwise comparisons, so I want to compare all the diets to each other, I can use this same code and just specify that I want pairwise tests. And now it will compare each of those weights to each other. And you can see there's a two-key adjustment here for this. But I can see, for example, probably I would consider diet 1 and diet 3 to be different from each other. And those are the lowest and highest weights. I think I want to show one more type of analysis before I end. And again, there's a little bit more in the lecture notes that I am not going to get to. That's basically some non-parametric analyses that you can use if you don't have normally distributed data. But I want to show you one more thing. I want to show you, you might think of it as an ANCOVA or just a general linear model. One of the things that's important about the chicks in this, looking at the diets, is not just, are the diets, are they different from each other at week 2, or sorry, at week 3, which is weight 2. But what if I account for how big they are when they're born? Does that make a difference? So I can include not just diet, which is a categorical variable, but I can also add their weight when they're born as a covariate to see if that has a relationship to their weight at week 3. And also to see if that helps, I'm going to call this model 3, if that helps to help me to get a better idea of the effects of the diets after I account for their weight when they're born. So I've run the model. Again, it's sort of strange if you aren't used to R to see that there's no output initially, but that's why we want to look at the ANOVA and the summary. So I'm going to say ANOVA for model 3. There's actually not a statistically significant effect of how much they weigh when they're born, which is not that surprising because they all weigh very much the same when they're born. But we still see a significant effect of diet, and I can still look at the summary. I can see that roughly if they're born smaller, they actually, so again, not statistically significant, but if they're born smaller, then they actually tend to weigh more at week 3. So not necessarily what you would expect. If they're born larger, they tend to weigh less at week 3. And we can also still look at, for example, at these estimated marginal means for the ANCOVA as well, just looking at diet. Okay. So we've gotten through quite a lot today. I know that, so far you've just been watching me do some things in R and seeing how it works. You haven't had a chance to try it out for yourself. Again, that's just very difficult to do when we're doing a Zoom workshop. But what have we covered today? So we started with some very basic things. We talked about RStudio and everything we have available in RStudio. We talked about how you can set a working directory so you can access specific files on your computer through R. We talked about how you read in data and make it an object in your environment so that you can use it in R. I showed you how to make comments, which can be very important when you are writing a program, so you remember what you did. Don't forget to save your syntax, so you can come back to this over and over again. And then we started with summary statistics. So summary statistics for numeric variables, for categorical variables. Then we looked at some things that summarize relationships between variables. Then we looked at some actual inferential tests. We looked at t-tests. We looked at chi-square tests and McNamara tests, Fisher tests. And we ended with t-tests and regression, ANOVA, and general linear models. So we've actually seen quite a lot today, and I know you still need a chance to practice that. Again, you have files with all of the examples or all the examples in it that I did today, and you have a separate exercises file that you can use. So you can try all of these things for yourself, kind of following along. And we also have recorded this video for today, so you can rewatch anything that I did and maybe hear a little bit better if you didn't have a chance to hear it today. So I'll go ahead and end there. And again, if you have questions about this or when you go through the exercises, you can always talk to Professor Awe. And I guess if there's any final questions for me, I would be very happy to answer those before we end.
Any question?
Okay.
Thank you, Kim. Let's thank our presenter.
Okay.
Thank you so much, Kim. Thank you for listening.
Thank you all very much for having me.
Thank you, Kim. Thank you, Kim.